Hello and welcome to this third lecture on thick-walled pressure vessels. In the first of the lectures we outlined the theory behind Lamè's equations that are used to solve for stress distributions across a thick-walled cylinder. In the second lecture we further derived some equations that we use in the solution of thick-walled pressure vessels. In this lecture we just continue with applications of thick-walled pressure vessels. So it's assumed you've seen the previous lectures associated with this topic area. This video is designed as a self-learning video where I will show you various questions. I will outline the questions to you. I will then suggest that you solve the questions, but there will be full work solutions presented to the majority of the questions in this presentation. Here's a recap of thick cylinder theory, summary of the equations shown here. Initially we'll be using the Lamè's equations we derived previously. The radial stress equation shown here is equal to A minus B upon R squared, and the hoop stress equation shown here is A plus B divided by R squared. Those are Lamè's equations for the radial and the hoop stress respectively. So the first batch of questions will use those equations. Don't forget we have to solve for the unknown constants A and B. We'll be given various parameters in each of the questions that will form boundary conditions at either the inside surface or maybe the inside and the outside surface, depending on the information given. And we'll solve simultaneously for constants A and B to find Lamè's equations. Then we can find the radial stress or the hoop stress throughout the vessel thickness. Some questions may also require us to calculate the longitudinal stress. We've got two formulae here for longitudinal stress. The first one has an internal and an external pressure applied to the vessel, but the second one just has an internal pressure. The external pressure is assumed 0. And remember, we're always using gauge pressures here. And later questions may want us to calculate the maximum shear stress in the vessel wall. And again, we've got two equations we derived previously to calculate the maximum shear stress in the pressure wall. And finally, we may be asked to calculate the change in diameter or the change in length. So to find the change in diameter, we'll first need to calculate the hoop strain. And that's given here by generalized Hooke's law for a triaxial stress situation. And we may also be asked to calculate the change in length of the vessel, so we need the longitudinal strain, and again that's shown here in terms of generalized Hooke's law. Remember, we are considering a triaxial stress situation when we're analysing thick-walled pressure vessels. If we want to find the actual change in diameter, then of course it will be the hoop strain multiplied by the original diameter. And if we want to find the actual change in length, then it will be the longitudinal strain multiplied by the original length. So here's the first question, question 1. A cylindrical compressed air drum has an external diameter of 2 meters and an internal diameter of 1.975 meters. If the internal pressure is 2 megapascals, we're asked to calculate the hoop stress within the cylinder wall at the bore, at the mean radius and at the outside surface, using Lamè's equations. In this particular question, for comparative purposes, we're asked to also calculate the hoop stress using thin cylinder theory. What you'll notice with this particular question is that the pressure vessel is a thin-walled vessel. The D upon T is greater than 20. The answers are shown in the brackets, and you can clearly see that the outside hoop stress, the mean diameter hoop stress, and the inside hoop stress are very, very similar. And that's what you would expect if you refer back to our presentation on thin-walled pressure vessels. What we've got to do here is apply Lamè's equations for the conditions given, evaluate our constants A and B, and form our radial and hoop stress equation. And in this particular case, we just need to work out the hoop stress across the cylinder wall. We'll then compare it to the thin cylinder theory. If you think you can attempt this question, I'd encourage you to stop the presentation and attempt it now. But on the next slide, I show extracted information from the question just to get you started. So it's question 1. Here's the start of the solution. I've extracted various information from the question. We've got the outside diameter, capital D, I've labelled it as is 2 meters, the inside diameter 1.975 meters. There's no external pressure stated, so we will assume the outside pressure is 0 gauge, and the inside pressure is given as 2 megapascals. That's 2 times 10 to the 6 newtons per meter squared, and of course all our pressures are gauge here. So I can easily calculate my outside radius, that's 1 meter in this case, my inside radius 0.9785 meters, and I can calculate my mean radius 0.99375 meters. For reference, the wall thickness can be calculated, and that's 0.0125 meters. If I check the D upon T ratio, I find that the inside diameter divided by the wall thickness is 158, so definitely a thin cylinder because it's very much greater than 20. So what I would encourage you now to do is start the presentation and apply Lama's equations, calculate the constants A and B, and then work out from Lama's equations the hoop stress distribution across the pressure wall. We need to work out the hoop stress at the bore, which would be the maximum, at the mean radius, and at the outside surface. I'd encourage you to start the presentation and attempt this question now, but the full work solution is shown on the following slide. So here's question 1. The boundary condition in this particular case, the radial stress at the outside surface would be 0 because there's no pressure applied to the outside surface, and the radial stress at the inside surface equal and opposite to the pressure applied, so it would be negative 2 times 10 to the 6 newtons per meter squared. So we now have 2 locations across the pressure wall where we know the stress. So applying Lama's equation for the radial stress at the outside surface, that will be 0 is equal to A minus B divided by the outside radius, which is 1 squared. That simplifies obviously to 0 is equal to A minus B. Call that equation 1 here. Now apply Lama's equation for radial stress, this time at the inside radius, at the bore of the vessel. So now we know the inside radial stress is negative 2 times 10 to the 6. We've got our inside radius. So we can evaluate then equation 2. Okay, notice I'm putting my equation onto one line, so the 1.02547 is actually 1 divided by 0.9875 squared. If you refer back to our previous presentation, I often remove the fractions in the equations. So question 1 continued. So solving the equations simultaneously, then we have equation 1 minus equation 2. Solving, that gives a value of constant B is equal to 78.493, and that's meganewtons in this case, or times 10 to the 6. If we back substitute the value of B into, and I'm using equation 1 here, you can use any equation you want to, we find that constant A is 78.493, and that's meganewtons per meter squared. So now we have Lama's equations. If we want the radial stress equation, sigma r, it would be the A value minus the B value divided by the radius squared. In this particular case, we're interested in the hoop stress. So our hoop stress equation, sigma h, is equal to the A value plus the B value divided by r squared. And there's a hoop stress equation we're now going to use. Question 1 continued. So for completeness, I did actually undertake my radial stress calculations throughout the cylinder wall. So radius of 1 meter, putting 1 meter into the radial stress equation, we find the radial stress is 0, which of course it is. That was a boundary condition. Then putting my mean radius into the radial stress equation, I get negative 0.99 meganewtons per meter squared. And then putting my internal radius into the radial stress equation, I get negative 2 meganewtons per meter squared, which again, of course, is a boundary condition. So that's just for reference, really. It's a hoop stress we're actually asked to calculate through the cylinder wall. So at the outside radius of 1 meter, putting 1 meter into the hoop stress equation, the hoop stress is 157 meganewtons per meter squared. Inserting the mean radius into the hoop stress equation gives a value of 158 meganewtons per meter squared, and the inside radius at the bore inserting that radius into the equation, 159 meganewtons per metre squared. And it's not surprising that the hoop stress is very little across the vessel wall, because this is actually a thin cylinder. We know an assumption made in thin cylinder theory is that the hoop stress is constant across the vessel wall, and we can see it essentially is constant in this case. I'm just showing you this formula for reference. It's called the mean diameter formula. Now in this particular case for question 1, an approximate analysis can be shown to be applicable for calculating the hoop stress, as this was a thin cylinder. So we could calculate the hoop stress from the PD upon 2T, the formula we used in a previous presentation related to thin cylinders, where P is the internal pressure, DI is the internal diameter, and T is the wall thickness. However, I was informed by a pressure vessel engineer a few years ago that in the pressure vessel design codes, they have used this relationship, but using the mean diameter, dm here, replacing the internal diameter, di, in the above equation. There's no theoretical justification for this so-called mean diameter formula, but as can be seen from the graph shown below, it does appear to provide a good approximation to Lami's hoop stress at the bore for cylinders with a di upon t ratio down to 5. So what this graph is trying to show that if we use PD upon 2T, where the D is the internal diameter for thin cylinder theory, then the percentage error is quite large when we have low D upon T ratio. This is my D upon T ratio. So we've got quite large percentage errors, 20% here at around about a D upon T ratio of 5. But if we use the mean diameter in the thin cylinder equation, PD upon 2T, we can see that the percentage error for the hoop stress at the bore reduces considerably. In about a D upon T upon 5 ratio, it's in the region of 3% error. So when you think of the work involved in calculating the hoop stress at the bore from Lami's equations and compare it to using the PD upon 2T formula, you can see that the mean diameter formula is a useful check we can apply when analysing thick-walled pressure vessels with internal pressure. So that's just for reference and an equation we can use just to check out the hoop stress at the bore should we want to. This question 1 continues. I'm applying the mean diameter formula here just to show how it works. So we have hoop stress is P multiplied by the mean diameter divided by twice the thickness. So all I'm doing here is putting in the internal pressure, the mean diameter over twice the thickness given in the question, and that worked out to be 159 meganewtons per metre squared, exactly what we calculated from Lami's equations after solving the simultaneous equations. And obviously if we check that with thin cylinder theory, in this case we know that will be the same value because we've got a very, very thin wall vessel here. So using the inside diameter, and of course we'll get very, very similar values, 158 meganewtons per metre squared. So for thick-walled vessels, if we want to check our hoop stress at the bore with internal pressure applied, we can use the mean diameter formula. So question 2, there's 2 parts to this question. Part A steel pipe of internal diameter 50 millimeters and wall thickness 20 millimeters is subjected to an internal pressure of 15 newtons per millimeter squared. We're asked to determine the hoop and radial stresses at the inner and outer surfaces of the pipe using Lami's equations. We have to state the type and the location of the maximum stress within the pipe wall. Part B. If thin cylinder theory had been used to determine the hoop stress, we've got to calculate the percentage error between thick and thin cylinder theory. We need to use the internal diameter in the thin cylinder formula. The answers are given in the brackets here. So the first part of question 2 is quite similar to that undertaken in the previous question 1. If you think you can attempt the question without further assistance, I would encourage you to stop the presentation and attempt it now, but on the next slide I will start the solution of question 2. So question 2, here's the beginning of the solution. The first thing we need to do is to extract the information from the question. So in the question we're given an internal diameter of 50 millimeters, a wall thickness of 20 millimeters. So that allows me to calculate the outside diameter. That will be the inside diameter plus twice the wall thickness. So the outside diameter is 90 millimeters. The external pressure on the vessel is 0 gauge, and the internal pressure is given as 15 newtons per millimeter squared. We can now calculate the outside radius, our naught, that's 45 millimeters, and the inside radius, that's 25 millimeters. The mean radius is the average of the outside and inside radius, so that's 35 millimeters. Checking the D upon T ratio, the inside diameter divided by the wall thickness is 2.5, so that's less than 10. So thick cylinder theory applies here. I'll encourage you now to apply the two boundary conditions. We know the internal pressure, so we have the inside radial stress, and we know there's no pressure applied at the outside, so the radial stress at the outside surface is 0. Knowing those two boundary conditions, we can now solve for constants A and B, and we can generate our radial and our hoop stress equations. From there we can find the stress at any location through the vessel wall. I'd encourage you to stop the presentation and solve this problem, but the full work solution is shown on the following slides. So question 2 solution continued. Here's our boundary conditions from the question. We know the radial stress at the outside surface is 0, and the radial stress at the inside surface is equal and opposite to the pressure, so it's negative 15 newtons per millimeter squared. Applying Lama's equations for the radial stress at the outside surface, generate equation 1. Notice again I've written this equation onto one line, so the 0.000494 is actually 1 divided by 45 squared. That's usually my approach to remove the fraction. And similarly we can find the radial stress at the inside surface. We know the pressure at the inside is negative 15 newtons per millimeter squared. So equation 2 can be derived. So now I've got my two equations, I can solve them simultaneously to find constants A and B. Question 2 continued, so solving the equations simultaneously, equation 1 minus equation 2 in this case, we find that constant B is 13,562 newtons, and back substituting value of B into equation 1 in this case, we find constant A is 6.697 newtons per millimeter squared. So we now have Lama's equations. For the radial stress, it's 6.697 minus 13,562 divided by r squared. And for the hoop stress, it's the same numerical values but with a plus between them. Question 2 continued. I've calculated now the radial stresses through the cylinder wall. So at the outside surface, 45 millimeters, we know the radial stress is 0, and that's what it calculates to be. That was a boundary condition. At the mean radius, 35 millimeters, put in 35 into the radial stress equation. The radial stress is negative 4.37 newtons per millimeter squared. And at the inside surface, and the radius is 25 millimeters, and 25 into our equation, we find the radial stress is negative 15 newtons per millimeter squared, and of course that was a boundary condition. So a little check on our solutions there. And then calculating the hoop stresses through the cylinder wall, very similar process, just use the hoop stress equation. So again, R0, 45 millimeters, put in 45 into the equation. So 13.4 newtons per millimeter squared is the hoop stress at the outside surface. At the mean radius, 35 millimeters, hoop stress is 17.8 newtons per millimeter squared. And at the inside radius, the bore, 25 millimeters, the hoop stress is 28.4 newtons per millimeter squared. Question 2 continued. This slide actually shows the distribution of the various stresses across the pressure wall. So the hoop stress distribution, sigma h here. Hoop stress is maximum at the bore, 28.4 newtons per millimeter squared, or 28.4 meganewtons per meter squared is shown on a diagram. At the mean radius, hoop stress is 17.8 newtons per millimeter squared, and at the outside surface it was 13.4 newtons per millimetre squared. Considering the radial stress, the sigma r, we know at the bore it's equal and opposite to the pressure. The pressure was 15 newtons per millimetre squared. So the radial stress is negative 15 newtons per millimetre squared. At the mean radius, it's negative 4.37. At the outside surface, it's 0. So this diagram shows the nonlinear hoop distribution across the vessel wall and the nonlinear radial stress distribution across the vessel wall. Question 2 continued. I've just used the mean diameter formula here to check for the hoop stress at the bore. So the hoop stress at the bore would be PD upon 2T, where of course the diameter in this case would be 70 millimeters. That's the mean diameter of the pipe, and that evaluates to 26.25 newtons per millimeter squared. If we check that with the maximum hoop stress from Long's equation, that was 28.4 newtons per millimeter squared. So a reasonable estimate from the mean diameter formula. Part B of question 2 asked us to use thin cylinder theory to evaluate the hoop stress. So hoop stress from thin cylinder theory would be PD upon 2T, where this time we use the internal diameter of the pipe, which is 50 millimeters. That evaluates to 18.75 newtons per millimeter squared. If we now do a comparison between thin and thick cylinder theory, our thick cylinder hoop stress at the bore was 28.4 newtons per millimeter squared. From above, the hoop stress from thin cylinder theory was 18.75 newtons per millimeter squared. So that evaluates to a percentage error of 34%. So we can see for small d upon t ratios, thin cylinder theory cannot be used. It gives very inaccurate results. Question 3. Slightly different solution process this time. A cylinder of a hydraulic actuator, the type we looked at in the previous presentation, has a bore and inside diameter of 0.1 meters. It's required to operate up to an internal pressure of 245 bar. We're asked to determine the required wall thickness to the nearest millimeter if the actuator is made from steel, have an ultimate tensile strength UTS of 360 meganewtons per meter squared, and a factor of safety of 5 is to be applied to the material UTS. If the ultimate shear strength for the material is assumed to be 60% of the ultimate tensile strength, we've got to calculate the factor of safety against the ultimate shear strength. So 2 calculations there. So effectively what you're given in the question are 2 boundary conditions again, but in this case they both relate to the bore of the vessel. You actually have a radial stress at the bore equal and opposite to the pressure applied, but you're also going to have a maximum hoop stress at the bore because that's limited to 1/5 of the ultimate tensile strength. So those are your 2 conditions in this particular question. If you think you can attempt the question from here without further assistance, I would encourage you to do so. But I will extract the information from the question on the following slide to start the solution process. So here's question 3, the beginning of the solution. So in this particular question, an unknown is the outside diameter. We do not know the outside diameter. In all previous questions, we've been given the outside diameter, the outside radius, but this time we do not know. We're trying to find it because we need to determine the wall thickness in the question. We know the inside diameter, it's 0.1 meters. In this case, the external pressure is shown to be 0, and the internal pressure is 245 times 10 to the 5 newtons per meter squared. That's 245 bar. Don't forget bar is 10 to the 5 pascals. The inside radius we can calculate from the question, that's 0.05 meters, and we're given a factor of safety against the ultimate tensile strength of 5. Again, from the question, the ultimate tensile strength is 360 times 10 to the 6 newtons per meter squared. That's the 360 meganewtons per meter squared. So now we can calculate the permissible hoop stress, sigma h, at the bore. Don't forget the hoop stress in this case will be highest at the bore. So that will be limited to 1/5 of the ultimate tensile strength. So 360 times 10 to the 6 divided by 5 of 72 times 10 to the 6 newtons per meter squared. So that's the maximum hoop stress we're allowed to apply at the vessel bore. The question also wants us to calculate the factor of safety against the ultimate shear strength. And we're told in the question the ultimate shear strength is 60% of the ultimate tensile strength. So that's a typical value. So the ultimate shear strength is 216 times 10 to the 6 newtons per meter squared. We'll need that later on. So what I encourage you to do now is stop the presentation and attempt this question. You again have two boundary conditions, but they both relate to the bore in this particular case. We know the radial stress at the bore, it's equal and opposite to the pressure, and we also this time know the hoop stress at the bore. The hoop stress is 72 times 10 to the 6 newtons per meter squared. So those are the two boundary conditions we can now use to find the constants A and B in Long's equations, and then using the radial stress equation we'll be able to calculate the thickness of the vessel wall, because we know the external pressure has to be 0. I'd encourage you to stop the presentation and take this question, but the full work solution is shown on the following slides. Question 3, solution continued. So here are our boundary conditions, both this time at the inside radius of the vessel. So the hoop stress from the previous slide is 72 times 10 to the 6 newtons per meter squared. And the radial stress at the inside is equal and opposite to the internal pressure. That was negative 24.5 times 10 to the 6 newtons per meter squared. So the way we generate our simultaneous equations, exactly the same process, it's just that they're both at the inside radius. So hoop stress at the inside radius, that forms equation 1 shown here. And then the radial stress at the inside radius, that forms equation 2. Question 3, solution continued. Again, solving the simultaneous equations as before. Constant B in this case evaluates to 120,625 newtons. Back substituting that into, in this case, equation 1, constant A evaluates to 23.75 meganewtons per meter squared. So that allows us to generate the radial stress equation. That's the A minus the B divided by the R squared. And of course the hoop stress equation, that's the A plus the B divided by R squared. Now what we're going to do is find the vessel wall thickness using the radial stress condition at the outside surface. Question 3, solution continued. So let's calculate the outside radius of the vessel from the radial stress equation. At the outside surface, we're going to assume that the gauge pressure is 0 because nothing's stated in the question for external pressure. So that means the radial stress at the outside surface is 0. So from the radial stress equation, 0 is equal to the A minus the B divided by the outside radius squared. All we're going to do now is rearrange the equation for the outside radius. So transposing the equation for R0, I would add this term to both sides of the equation. Then I would multiply both sides by R0 squared and divide both sides by 23.75 times 10 to the 6. That will then form the equation R0 is equal to the square root of, in brackets, 120,625 divided by the 23.75 times 10 to the 6. That evaluates to an outside radius of 0.0713 meters. We can then calculate the thickness of the vessel. So the thickness is simply the outside radius minus the inside radius. That evaluates to 0.0213 meters or 21.3 millimeters. So to the nearest millimeter, we need to use 22 millimeters. That's an outside radius of 72 millimeters. So let's just check the D upon T ratio as we now know the thickness. So the internal diameter is 0.1 meters. Conservatively, I'm using the 0.0213 meters calculated thickness. That gives a D upon T ratio of 4.7, which is very much less than 10. So thick-walled cylinder theory applies here. Question 3, solution continued. So we're asked to calculate the maximum shear stress in the cylinder wall, and that will occur at the bore. So the equation I'm using here is taken from our summary slide shown at the start of the presentation. I'm going to use this equation, the shear stress. So maximum shear stress then is 72, that's the hoop stress at the bore, minus the negative 24.5 radial stress, notice the double negative there, and that's all divided by 2. So 47.5 meganewtons per meter squared is the maximum shear stress in the vessel wall, which occurs at the bore. We're asked to calculate the factor of safety against the ultimate shear strengths. We calculated the ultimate shear strengths previously to be 216 meganewtons per meter squared, so dividing that by 47.5 above, we get a factor of safety in shear of 4.5. Question 3 continued. This is purely for reference. I did calculate the radial stresses throughout the cylinder wall and the hoop stresses throughout the cylinder wall, but the question didn't actually ask for those, but there they are for completeness. Question 4. A thick cylinder has an internal diameter of 400 millimeters, an external diameter of 600 millimeters. If it has closed ends and is subject to an internal pressure of 70 megapascals, and in this case an external pressure of 40 megapascals, we have to calculate the following. Part 1, we have to calculate the radial and hoop stresses at the inner and outer surfaces of the cylinder. Part 2, we have to calculate the longitudinal stress if the cylinder is assumed to have closed ends. And part 3, we've got to calculate the maximum shear stress in the vessel wall. So a difference here is that we have an external pressure as well as an internal pressure. So the only thing that's slightly different in this particular case when generating our equations is that the radial stress at the inside surface will be negative 70 megapascals because that's equal and opposite to internal pressure. But notice here we have an external pressure of 40 megapascals. So our outside radial stress will actually be negative 40 megapascals, not 0, which we usually assume when we have no external pressure stated. So that's the only thing that's different in generating the equations. We actually have a value for the radial stress at the outside surface. So we'll be able to determine our constants A and B, and so our Lamy equations, and then we can calculate the radial and hoop stress as required in part 1. Part 2 wants us to calculate longitudinal stress, and we have an equation for longitudinal stress in our formula sheets. And then part 3 wants to calculate the maximum shear stress in the vessel wall, and again that will occur at the bore, and we have an equation for calculating the maximum shear stress. The answers are shown in the brackets here, and if you think you can attempt the question without further assistance, I would strongly encourage you to stop the presentation now and attempt the question. But on the next slide I will extract the information from the question to start the solution. So question 4. Here's the commencement of the solution. In the question we're given the outside diameter. It's actually 600 millimeters in the question. I've converted that to meters, so 0.6 meters. We're given the inside diameter, 400 millimeters, and again put that into meters, 0.4 meters. In this particular question we do have an external pressure. It's 40 megapascals. We have an internal pressure of 70 megapascals. So from the geometry I can calculate the outside radius, it's 0.3 meters, the inside radius 0.2 meters, the wall thickness calculates to 0.1 meters, and I've got my mean radius of 0.25 meters. Just check the D upon T ratio, that will be the inside diameter 0.4 divided by the wall thickness 0.1, so the D upon T ratio is 4, so that's much less than 10, so thick cylinder theory applies. So what we need to do now is generate the simultaneous equations. They'll both be for radial stress. At the inside radius, we know that the radial stress will be negative 70 megapascals. At the outside radius, we know the radial stress will be negative 40 megapascals in this case, and from there we can generate constants A and B, and so our equations for radial and hoop stress. I would encourage you to start the presentation and attempt this question from here, but the full work solution is shown on the following slides. So question 4, solution continued. So here's our boundary conditions, both in terms of radial stress, but at the inside and outside of the vessel. So at the outside of the vessel, the radial stress is negative 40 megapascals. At the inside of the vessel, the radial stress is negative 70 megapascals. That allows us to generate our two equations. So considering the radial stress at the outside surface, generate equation 1, and considering radial stress at the inside surface at the bore, that generates equation 2. Question 4, solution continued. So solving our simultaneous equations, I find constant B is 2.16 meganewtons. Back substituting the value of B into equation 1, I find constant A is negative 16 meganewtons per meter squared. Notice that the constant A is negative in this particular case. That allows us to generate Lammer's equation. So for the radial stress sigma r, it's negative 16 minus 2.16 divided by r squared. And for the hoop stress equation, it's negative 16 plus 2.16 divided by r squared. I can now find the radial and hoop stresses across the vessel wall. Question 4, solution continued. I've calculated my radial stresses through the cylinder wall. I'll let you check them at your convenience. And I've calculated my hoop stresses through the cylinder wall. And again, I'll let you check them at your convenience. Question 4, solution. We're asked to calculate the longitudinal stresses in the cylinder wall. From our previous presentation, we assumed the longitudinal stresses to be constant across the wall. And because I've got internal and external pressure, I'm using this equation extracted from our summary. So this equation, because I have both the internal and the external pressure to consider in this particular question. So inserting the values into the equation, we calculate sigma L, and that becomes negative 16 meganewtons per meter squared. So we've got actually a compressive longitudinal stress in this particular case because we've got external pressure in the vessel over the outside surface. Finally, we're asked to calculate the shear stress in the vessel wall. That's the maximum at the bore. So again, from our previous equation, the maximum shear stress will be the hoop stress at the bore minus the radial stress at the bore divided by 2. The hoop stress at the bore is 38 meganewtons per meter squared. The radial stress is negative 70 meganewtons per meter squared. Again, the double negatives there, be careful. That evaluates to 54 meganewtons per meter squared as the shear stress at the bore. In question 5, I'm going to leave for you to attempt at your own pace. For the thick cylinder shown in the sketch, having an external pressure of 50 newtons per millimeter squared and an internal pressure of 10 newtons per millimeter squared, we're asked to plot the hoop stress and the radial stress distribution across the vessel wall. The external and internal diameters of the cylinder are given as 400 millimeters and 250 millimeters respectively. Assuming that the vessel has closed ends, we're asked to calculate the longitudinal stress and also the maximum shear stress in the vessel wall. The answers are stated in the brackets. I would encourage you to stop the video and attempt this question and work it through at your own pace, using the previous work we've considered in this presentation to help you with your solution. Question 6. A hydraulic cylinder has an external diameter of 100 millimeters and a wall thickness of 20 millimeters. We're asked to determine the radial and the hoop stresses at the inside and outside surfaces of the cylinder when it is subjected to an internal pressure of 1000 bar. If the vessel has closed ends, we're asked to calculate the longitudinal stress, and this time the change in thickness that's occurred. Its modulus is stated as 205 gigapascals and the Poisson's ratio is 0.29. The answers are shown in the brackets. So the first part of question 6 commences in the same way as previous questions. We need to find our boundary conditions, generate two equations, solve to find Lammer's equations for radial and hoop stress, and we can calculate the radial and hoop stresses at the inside and outside surfaces. And as before, if we want to calculate the longitudinal stress, which is assumed constant across the vessel wall thickness, we have a formula to do so. But this time it also wants us to calculate the change in thickness that's occurred. So that means we will need to calculate the diametrical or the circumferential strain. So that will mean we have to calculate the diametrical strain for both the inside and outside diameters, from which we can find the change in diameters, and then calculate the change in thickness of the vessel wall. If you think you can attempt this question without further assistance, I'd encourage you to stop the presentation and do so, but I will work through the full solution on the following slides. So question 6, here's the commencement of the solution. Extracting the information from the question. I'm using millimeters this time, so my inside radius and outside radius in millimeters. And notice I've converted the internal pressure of 1000 bar into newtons per millimeter squared. So the internal pressure is 100 newtons per millimeter squared. I did use a unity bracket conversion shown here for reference. So we'll be using Lambert's equations here for the radial stress, the A minus B upon R squared, and for the hoop stress, the A plus B upon R squared. Question 6, solution continued. So we need to calculate the constants A and B as always from the boundary conditions given. And the boundary conditions are that the radial stress at the inside surface is negative 100 newtons per millimeter squared, and the radial stress at the outside surface, we're assuming that to be 0 because no pressure applied. That generates our two equations, which again we solve simultaneously, and we calculate the value of constant B to be 140,625 newtons, from where we can find constant A, which is 56.25 newtons per millimeter squared. So now we can write our radial stress using our constants A and B. That's 56.25 minus 140,625 divided by R squared. And the very similar equation for the hoop stress is just that there's a plus between the two terms. So question 6 continued, calculating the stress at the bore when the R is equal to 30. Putting 30 into our radial stress equation. We find that the radial stress is negative 100 newtons per millimeter squared at the bore, which of course it should be, that's our boundary condition. And putting the 30 squared into the hoop stress equation, we find the hoop stress at the bore is 212.5 newtons per millimeter squared. If we now consider the stresses at the outside surface when R is equal to 50 millimeters, in the 50 millimeters into the radial stress equation, the radial stress is 0, which it should be for the boundary conditions, so that checks. And putting the 50 into the hoop stress equation, we find the hoop stress at the outside is 112.5 newtons per millimeter squared. The question also asked us to find the longitudinal stress, sigma L, and we have an equation for that. And I've used a simplified equation here when just an internal pressure is considered. Put in the internal pressure of 100 newtons per millimeter squared. The longitudinal stress assumed constant across the vessel wall is 56.3 newtons per millimeter squared. So question 6 solution continued. We were asked to find the change in thickness. So to do that, we need to calculate the hoop strain at the bore, from which we can find the new diameter of the bore. And then we'll find the hoop strain at the outside surface, which we'll find the diameter at the outside surface, and from that we can find the change in thickness. So first of all, hoop strain at the bore. Remember that thick cylinders is a triaxial stress situation, so I'm using generalized Tooke's law in 3 dimensions. So to calculate the hoop strain is equal to the hoop stress divided by E minus the Poisson effect of the radial stress divided by E minus the Poisson effect of the longitudinal stress divided by E. All I've done on the next line is factorize the equation to make the calculation slightly easier to perform. But evaluating my hoop strain at the inside surface at the bore, so that's 0.0010988, or rounding up, that's 1099 microstrain. So to find the change in diameter at the bore, the hoop or diametrical strain at the bore is a change in diameter over the original diameter. Rearranging, the change in diameter is equal to the hoop strain multiplied by the original diameter. Inserting our values for the strain, original diameter is 60 millimeters. We find a change in internal diameter of 0.066 millimeters. We now undertake a similar process to calculate the hoop strain at the outside surface of the vessel. Hoop strain at the outside surface can be calculated from the equation shown here, as used before, and that's 0.004691, or 469.1 microstrain. So again, we can find our change in diameter at the outside surface. That will be the hoop strain at the outside surface multiplied by the original outside diameter. Evaluating that becomes 0.0469 millimeters. And the change in thickness, it's simply the change in the outside diameter minus a change in the inside diameter divided by 2. Evaluating, we find the change in wall thickness to be approximately negative 0.01 millimeters. In other words, a reduction in wall thickness. And if we wanted to calculate the final diameters of the vessel when pressurized, the final inside diameter would be the original inside diameter plus the change in diameter we've calculated. So the final inside diameter is 60.066 millimeters. And if we wanted to calculate the final outside diameter, that would be the original outside diameter plus the change in the outside diameter calculated. So the final outside diameter is 100.0469 millimeters. Question 7, I will leave you to attempt. You've got a closed-ended 6-cylinder, has an internal diameter of 50 millimeters, an external diameter of 100 millimeters. Given an internal pressure of 400 bar, we'll assume the external pressure is 0. We've got to determine the change in internal diameter of the cylinder. So a similar kind of approach as shown for question 6. We need to work out the diametrical hoop strain. We're given the E value for the material and the Poisson's ratio. Answer is shown in the bracket on the right hand side. I'll encourage you to stop the presentation and attempt this question. And question 8, I will leave you to attempt. In this question you have to determine the dimensions of the internal and external diameters and the change in the wall thickness from the unpressurized to the pressurized state. The answer is 4 micrometers. I would encourage you to attempt that question. And here's the bibliography used to help generate this presentation. I hope this presentation was of interest to you, and thank you for viewing.